Hello and welcome to the 8.2 notes. This is a unit that we'll call differential equations. So let's write that up here, that this is called differential equations. Okay. And a differential equation, there's a whole unit of study on it. We can take a class over it. We're going to do a very, very limited amount of work with it. But these are equations with derivatives in them. So with derivatives in them. Okay, and what we're going to do is we're going to draw this thing called a slope field. And a slope field is a way for us to visualize what the derived function looked like. So we have this differential equation. We can use this to help us visualize what the original equation looked like, okay? So what I want to do in order to draw a slope field, we need to draw a table here. And I'm going to draw a 3-column table. And I'm going to call this column X, this column Y, and this column dy dx. Now remember what dy dx is, okay? This is really y prime. This is really f prime of x. This is the derivative. Now remember what the derivative is. The derivative represents the slope of the tangent line at any x value, okay? In this case, because we're dealing with differential equations, we will be dealing with slopes at points, not just x values, but also x and y values. So the first point I want to do is the point 0, 0. Okay, so if I look at the point 0, 0 on the graph, this point right here, I want to know what is the slope of the tangent line at that point. So what I do is I plug in 0, 0 into my derivative, dy dx, and see what we get. And so I'm going to get that dy dx is equal to 0 minus 1, which gives me negative 1. Now this number here, negative 1, after I plugged in the point 0, 0, this is the slope of the tangent line at that point. So what I do is I come over to my slope field, and I'm going to draw a slope of negative 1, a tiny little slope, to show that I have a slope of negative 1 at the point 0, 0. Okay? Now, I'm going to start choosing some other points. I'm going to choose the point 0, 1, okay? And if I choose that point, the thing that I notice here is that I'm still just plugging in 0 into x of my derivative. So my derivative, dy dx, is going to equal 0 minus 1, and that's going to equal negative 1. So then I'm going to come over here to my slope field, and at the point 0, 1, I'm going to draw in a slope of negative 1. Now, what you should notice here is that at any point along my x-axis, or my y-axis, is that I will be plugging in a value of 0 into my differential equation. Since I'm plugging in a value of 0 into my differential equation, all right, because my differential equation does not contain a y value, I'm simply just going to get negative 1 any point along the y-axis. Okay, so there are patterns to this, and we want you to see those patterns. But I'm going to go ahead and just, at any point along the x-axis or the y-axis, I'm going to draw in a little slope of negative 1. Okay. Now let's kind of change directions. Let's look at and see what happens at any point along the line x equals 1. Okay, so if I plug in the point, say, 1, 0, okay, then if I plug that into my derivative, I get dy dx is equal to 1 minus 1. Okay, I'm simply plugging in this point into my differential equation to determine what my slope is. Now if I get 1 minus 1, that's just going to give me 0. So then I come over here, and at that point, 1, 0, I draw in a slope of 0. Okay? And then, let's go ahead and check out what happens at the point 1, 1. All right? So if I plug in 1, 1, then I'm going to get the same thing, okay? because I'm just plugging in 1 for x. The y value doesn't really matter. And so I get that dy dx is equal to 1 minus 1, which is 0. So at this point, 1, 1, I have a slope of 0. So I'm going to come in here and draw a little tick mark that shows me a slope of 0. Okay, and we can conclude that at any point along this line here, the slope of the tangent line is going to be 0 because I'm plugging in 1 for x. Okay? Now, this pattern is going to continue. So what happens if I plug in, say, something along this line, any point when x is equal to 2? Okay, so if I plug that in, if I plug in the point 2, 0, then my derivative value, okay, since x is 2, is going to be 2 minus 1, which gives me a slope of positive 1. Okay, so the pattern continues that I can come in here and draw in this slope of 1. Okay, and that's going to be true for any point along any of these points. I'm going to have a slope of 1. Okay, now what happens if I plug in a slope, or if I plug in a value of 3 into my derivative? Okay, and if I plug in 3, 0, then dy dx is going to be 3 minus 1, which gives me 2. Now this is a slope of 2. So I come in onto my slope field, and I'm going to draw in a slope of 2. Okay, and it's going to be a little bit steeper than the other points. Okay? And so we get this field of slopes. All right? Now the pattern is going to continue on the other side. If I plug in, say, negative 1, let's see what happens there. Let me make this a little bit bigger. So if I plug in the point negative 1, 0, all right, then that's going to give me dy dx is equal to negative 1 minus 1, which is negative 2. And so if I plug that in, I have a slope of negative 2, so this is going to get a little steeper, but the values are going to be negative. Okay? And so you kind of just eyeball it. You don't have to be exactly perfect. All right. And so let's check this next row. What happens if I plug in, say, negative 2, 0 into my differential equation? I get dy dx is equal to negative 2 minus 1, which is going to give me negative 3. All right, so then these slopes are going to get even more steep. Okay? And so we just draw these little tick marks in, and that's what we get. Now, if I plug in negative 3, okay, into my derivative, then negative 3 minus 1, that's going to give me a slope of negative 4. Okay? So it's going to be even more steep. Okay? So now the question is like, what's the point of this? Like, well, what does this picture even look like? Now, hopefully what you see is that these slopes kind of give you a general shape of something, and if you follow the slopes, then you actually get what we think it is, which is going to be a parabola. And so let's just think about something for a second, okay? If I had the differential equation dy dx is equal to x minus 1, well, isn't this, if I were to write my original function and take the antiderivative of that, wouldn't I just get x squared over 2 minus x plus c? Okay, and that's the idea, you know, I mean, any derivative that you have is a differential equation, and you get this, you know, general solution. I'm going to call this a general solution, okay? And, you know, the thing that I want you guys to see here is that when I have this slope field, this looks like the parabola x squared over 2 minus x. Now, we strictly depend on some initial condition on this graph to help us decide where this line goes. Now, let's just say, for example, that we have the initial condition. So I'm going to write that initial condition. Oh, let's just do the point, you know, 1, 0. All right, 1, 0. Doesn't really matter where it is. But if I have that initial condition 1, 0, I know that a point on my function is at 1, 0. So what I do then is I use this differential equation to help me draw my function, which is a parabola. And that's the whole point of this, okay? So we can use these slope fields to help us visualize what the original equation was and how to get it, okay? So let's go ahead and take a look at the next one. And this one's a little bit different because my derivative here, okay, dy dx is equal to 1/2 times y. Okay, this does not have a derivative, or it does not have an x value in it. So this one's a little bit different. But let's go ahead and let's create our table here for this one. Remember, we want to have an x column, a y column, and a dy dx column. Okay? And because my differential equation only contains y, the x values really don't matter a whole lot. But what I'm going to do is I'm going to go ahead and plug in the point 0, 0. I always start with the origin. And if I plug 0 into my differential equation, I get dy dx is equal to 1/2 times 0, which just gives me a slope of 0. So what I'm going to do is at that point, 0, 0, I'm going to draw in a slope of 0. Okay? And then the next thing I'm going to do is let's try and see what happens when I plug in the point 1, 0. So if I plug in the point 1, 0, my y value remains at 0. Then that's going to give me dy dx is equal to 1/2 times 0 again, so I just get 0. So what that does, at this point, I also have a slope of 0. So then if at any point along my y-axis, if I plug in a y value of 0, it's going to give me a slope of 0. So I can come over here and I can just draw in these little slopes of 0, and that's what I've got, okay? And then let's try another point on this. Let's try and plug in the point, say, 0, 1. And let's see what happens with that. So then if I plug that in, I get dy dx is equal to 1/2 times a y value of 1. And that's going to give me a slope of 1/2. So at the point 0, 1, at this point right here, I'm going to draw in a little slope of 1/2. So up 1 over 2. It's not going to be that steep, okay? And the pattern continues. And the pattern is that if I have a y value of 1, and if I plug it into my differential equation here, then I'm going to get a slope of 1/2, okay? And so I'm just going to go ahead and draw in this little slope of 1/2 at each of these points here, 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 and here, okay? So then what happens if I plug in a point of, something up here with a y value of 2? Well, let's check. Let's plug it into our table. So let's try the point 0, 2. So then dy dx is equal to 1/2 times 2, which gives me a slope of 1. Okay? So at any point when y is 2, we get a slope of 1. So let me come over here and let me draw those in. So they're a little bit steeper, a little bit steeper, a little bit steeper, all the way across. Okay? Now let's see what happens when I plug in a y value of -1. Okay, and you can probably guess what's going to happen, but if I plug in the point 0, -1, then I get dy dx is equal to 1/2 times -1, which gives me -1/2. Okay? And let's kind of think about what happens if I plug in a y value of -2. So 0, -2 gives me dy dx is equal to 1/2 times -2, which gives me a slope of -1. So we get this pattern down here. So this one was -1/2. All right. And we're just drawing these in. We're just sketching them in. They don't have to be exactly perfect. We want them to be reasonable. But that's about that. Okay. This column has a slope of -1/2. This one was a slope of 1/2. So a little bit steeper, 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 steeper. Now what I notice here is that I have this line here where the slopes would be 0 all the way across. This line right here is an asymptote, okay? This is a horizontal asymptote. All right, let me draw that in and label that this is a horizontal asymptote. okay? And the reason why I wrote that in is because depending on where my initial condition is, helps me figure out what this graph is going to look like. So let's say I have an initial condition up here, and let me change colors and do, let me do purple. All right, let's say I have an initial condition here, okay? If I were to use these slopes to help me draw my function, I'm going to get an exponential function up here that is concave up and curves up. So I'm going to get something that looks like this, okay? And that's what my function would look like if my point is above the x-axis. Now, if my initial condition, say, is below the x-axis, let's say I have an initial condition down here where I've got, say, a point on my original equation like that, then my function will behave a little bit differently, okay? So we might have these instances where, you know, our graphs look differently depending on where our initial condition is. Okay, but when you have a bunch of slopes that line up like this, that means that you have a horizontal asymptote. Okay, let's quickly take a look at the last one. Now this last one contains, this differential equation also contains x and y values. So let's go ahead and make our table here, and let's do an x column, a y column, and a dy dx column. Okay. And so let's go ahead and just plug in the point 0, 0. Okay, so then my dy dx value, okay, I'm going to plug in 0 for x, 0 for y. I'm going to get 0 minus 0, which just gives us 0. So when I get that, I'm going to come over here and plot a slope of 0 at 0, 0. All right, let's go ahead and plot the point 1, 1. And the reason why I'm doing that, I want to show you guys that there is a pattern here. When I subtract the x value minus the y value, if they are the same, then we'll get a slope of 0. So my dy dx value is equal to 1 minus 1, which gives us 0. Okay, so I'm going to come over here and draw a slope. I have a slope of 0 here. If I put in the point 2, 2, I get dy dx is equal to 2 minus 2, which gives me 0. And so we end up getting this pattern here that any point along these diagonals is going to have the same slope. So if I have negative 1, negative 1, I'm also going to have a slope of 0. Same with negative 2, negative 2. It's going to be a slope of 0. So I want you guys to see the patterns. Okay, now let's try the point 1, 0. Okay, if I plug that into my derivative, I get dy dx is equal to 1, which is my x value, minus 0, which is my y value, and that's going to give me a slope of 1. Now, what I've noticed here is that this gives me a slope of 1. Any point along this diagonal is also going to give me a slope of 1. So I'm going to have a slope of 1 here, 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 and here. And this is actually going to give me a slant asymptote, all right? But let's go ahead and let's see what happens if I plug in the point 2, 0. Okay, so if I plug in the point 2, 0, then I get dy dx is equal to 2 minus 0, which gives me a slope of 2. So then any point along here, these slopes get a little bit steeper, okay? And so there's my slope of 2. And here's my slope of 2, slope of 2, slope of 2, okay? So any point where your x value is 1 or is 2 larger than your y value, then that's what you're going to have happen on that line. Okay, and then let's plug in the point, say, 3, 0. And so my dy dx value is equal to 3 minus 0, which is a slope of 3. So every one of these, my slope gets a little bit steeper, okay? And so you can kind of assume that this next line here, this next diagonal, is going to have a slope of, 3. So then this is 4, even steeper, and this is 5, even steeper, okay? So now let's check to see what happens when I plug in, say, negative 1, 0. So I plug in negative 1, 0. then dy dx is going to be -1 minus 0, which gives me -1. So the pattern continues, but over here, okay, I have a slope of -1, -1, -1, -1, and -1. Okay? Then the pattern will continue. What's going to happen on this row? If this was -1, then this is going to be -2. So these slopes are steeper. -2, -2, -2, -2. Okay, this one is going to have a slope of 3. So make it a little bit steeper. Okay. And then this will have a slope of -4, so even steeper, and this one has -5. So you end up getting this, this slope field here, which does depend on where you have an initial condition. So remember, this will give you a depiction of what your function looks like. Now, I do want to come in here and say that this line right here is a slant asymptote, all right? So you do need to look for lines that the slopes go in the same direction, and if they connect to each other, then that's a slant asymptote. Now, if I plug in, say I have an initial condition up here at this point right here, all right, if I use the slope field to kind of help me find the curve of my line, all right, I should end up getting a function that looks like this, okay? Now, let's say that my initial condition is on the other side. Okay, let's say it's over here. Then my function is going to be a little bit different, okay? And so a slope field, just kind of tells us what these equations could look like, what the original equation looks like. But, we just have to use the slopes to kind of tell us that. So I hope that this was informative and you kind of know what's going on. This is a procedure. I know it's kind of a long video, but I'm going to go ahead and stop it where it's at, and we'll see you on the next one. Bye.